with warm greeting. Let's start with the first lecture in the subject digital signal processing. Okay, so first of all, moving ahead with the name has itself got three things where we have got a specific class of signal that we say a digital signal, then we have got signal, and then we have got processing on the signal. Okay, so moving ahead with the first major definition, that what is a signal. Okay, so if I give you a normal layman language of a signal is nothing but anything that conveys an information. Okay, so this is simply a kind of definition where we can say in normal layman language. Okay, now when we talk about going into the engineering details of it, any quantity represented in its graphical form. Okay, so let's just put it in the pen. A signal. Okay, let's go with this. So how we can say a signal define, or we can say a signal is a physical quantity that varies with time, space, or another independent independent variable. Okay, so what we can say, anything like, for example, let us say something. Here we have taken time and here we have taken voltage. So here what we define, we have a signal xt, okay, where we have voltage varying with time. Okay, so signal is basically, now what is this signal conveying? This signal is conveying an information that voltage is varying with time, and if I have to go in the mathematical form of it, so this is nothing but my x of t is, let us define this amplitude as a sine omega t. Okay, so this is what we call it as signal. So during your course of signal and systems, I expect that you must have you've been through different kind of signals where we have got continuous signal, discrete signal, digital signal, analog signal, power, energy, even, odd. There are n type of signals. Okay, so we are not going into the details of it, but according to the basics, first we'll discuss what there's a confusion between what is continuous and what is discrete. Okay, so let us start with simple bifurcation of signals. Okay, so any signal has two quantities. One is independent variable, that is time. Another is amplitude. Okay, so on the basis of time, we have got two types of signal. One is continuous and the one is discrete. Okay, and on the basis of amplitude, we have got analog and we have got digital signal. Okay, so how basically what these signals look like. So let us just try and form a kind of pictorial representation of these different type of signals. So let us just consider the first signal. Okay, this is my first signal. Okay, so let's put it as a, let's put it as x of t, and let's put it as t. I've got another signal. Put it as x of n, and let's put it as n. Then we've got another signal. And then let's put it as another form of signal. Minus 2. 2, 3. 1, 2, 3. This is again x of n, and this is again x of t. Okay, so what I'll say what my first signal is. My first signal is obviously an analog signal. So how this signal is represented as, this signal is represented as continuous in time and continuous in amplitude. Okay, now a second signal is a discrete signal, but again in analog form. Why? Because still we have continuous in amplitude, or rather let's go with the time first. Okay, so this signal is my discrete in time because my time is at a particular instance. I've sampled a signal, but it is still continuous in amplitude. So this class of signal is still analog. Okay, now here I have a signal which is continuous in time but discrete in amplitude, because I fixed the amplitude levels for 1, 2 and 3. Basically I've quantized this signal. Okay, so this signal is still this signal can be termed as digital signal, and here I have a signal which is discrete in time and discrete in amplitude. So this is also my digital signal. So basically when we represent signal, there are times when the students are asked what is the difference between continuous and analog signal. So basically we cannot compare the two quantity, continuous and analog, because when we talk about continuous and discrete, we are talking about time, and when we are talking about analog and digital, we are talking about amplitude. Okay, so sorry, this is what we can say about our basic signals. Okay, now during the course of the subject, there'll be another interesting questions for you. So the first interesting question is, the name of the subject that reads digital signal processing. But are we processing on a digital signal? That's the question. So we'll find out whether we literally talk about digital signal or we are talking about discrete. And if we are talking about discrete, why not the name of the subject is discrete signal processing? Okay, so the question is, it's digital or discrete? Okay, so we'll find out in the near future, and you'll be the one who'll be letting me know what kind of signal we are going to work on, either digital or discrete. And pardon me, and whether the information given to you is in digital form or a discrete form, and how you're going to differentiate. Okay, so going back to the recap of your same signals and systems concept, you must have studied about transforms. Okay, so when we talk about transform, what is a transform? Okay, so basic definition of transform in terms of your signals and digital and your engineering concept is changing from one form to another form. And when we talk about digital and digital signal processing, so basically we have a signal, naturally occurring signal are in time domain, time domain signal. We pass it through a machine called transform, be it be any. Okay, so it will convert itself into frequency domain signal. Okay, now the question arises, why frequency domain? Why do we need such kind of things? Because since we have got more powerful tools in mathematics because of the advent of your supercomputers and everything around, yet what we are doing, we are converting a time domain either from t or n to a frequency domain. Okay, either to omega or ohm. Okay, now one more thing, these two are frequencies but different frequencies. We'll get back to this, okay, in the near future. Okay, so we are basically converting a time domain to a frequency domain. Why? Okay, so this is a question for you, another part of question which I want you all to think. We'll surely discuss it. Why do we need transforms? हमें ज़रूरत क्या पड़ी transforms की? We have a powerful tool, we can process in time domain or everything, but yet I want to know about why do we need transforms. Okay, so we'll discuss that. Okay, now moving that into the types of transforms you have studied. So basically I will just draw a simple diagram. Okay, there's a diagrammatical representation that will help you understand what all transform you have studied and what all transform you'll be studying. Okay, so let us take, for example, let us start with, we have a signal x of t, so it's a continuous time signal. Okay, now when I sample this signal, when I sample this signal, what I do is I convert this signal into x of n. Okay, clear? Now if I sum, if I add the shifted replicas of this signal, what I'll do is I'll convert this signal into x p of n. that is nothing but a periodic signal. Okay, so what it is basically sum of shifted replicates. Alright everyone, so this you already know. Okay, now if I want to get it back, what I'll do is I'll just pass this signal to a band limited sync interpolation filter. This you have recently studied in your digital communication, right? Sync filter. Okay, and here what I'll do is I'll just pass it through a band limited rectangular window. Okay, clear everyone? So what is this band limited rectangular window? I'll just show it to you. Okay, let us say I have a digital signal, a discrete signal rather, like this. Okay, now again it repeats itself. Okay, so let us say this is my discrete signal. So what I need is what I'm doing in rectangular window, band limited rectangular window is I know this signal is going to repeat itself here and here. So what I'll do is I'll pass it through a band limited rectangular window filter where my filter response will be something like this. This is going to be my filter response. Because what is my xp of n? Xp of n is nothing but it is a same signal replicating itself in the next window, you can see. So what I'll do is I'll pass this signal of xpn, I'll pass this xpn to one of this window. I'll get my x of n. I'll again do interpolation and I'll get my x of t. Clear everyone? So this is what we're doing with a signal, but all this processing is being done in time domain. Okay, now comes my first powerful tool where I convert my signal. I'll pass through a Fourier transform. Okay, this time it's continuous time Fourier transform, and what I get is x of f. Now this is nothing but it is in the frequency domain. Here what I do is I pass it through a discrete time Fourier transform, and what I get is x of omega. Okay, here I have dt fs. This is Fourier series. Okay, now where what I reach x of k. Okay, and all these functions are reversible functions. So basically if I go with inverse of these functions, I get into my back to my original signal in time domain. Okay, now what are these xf, xn, x omega? These both are periodic signals. Okay, so this x of omega, if I specifically talk about this x of omega, this x of omega is still in continuous form and it's periodic in nature. Okay, now what is the problem with this continuous and periodic? We still have a problem here. Okay, so the problem with continuous and periodic is that we still cannot work perfectly on a continuous signal, because when we are going to quantize, the quantization error is going to take place. Okay, now when we are going to talk quantize, okay, for continuous signal we have infinite values in one domain. Okay, अब हमने क्या किया, we came from time domain to frequency domain. Okay, let us say to ease out the mathematical processing, yet I have got same repeated replicas. If you remember it, you used to get something like this magnitude replica. It was continuous and periodic. Okay, now to resolve this issue, we came up with another transform where, while moving from x of omega to x of k, what we did, we replaced omega, we got x of omega. How we got there? Where we replaced omega by 2 pi k by n. Now this is my DFT, discrete Fourier transform. Clear everyone? So let us just, okay, clear everyone? So, and similarly we had another transform where we had Z transform in discrete domain. So instead of landing up here, we could have landed up into x of z as well. X of z, you need to have properties of unit circle. I hope you remember. Then all poles should lie in, no pole should lie inside the unit circle, all poles should lie on the unit circle. All those properties of causal and non-causal, whatever you have studied. Okay, we are not going to into the details. So just a quick recap of what this diagrammatic representation is all about. Okay, so let us see. So we have continuous time Fourier transform. So I have x of AF in frequency domain from minus infinity to plus infinity, x of t e raised to the power minus j 2 pi ft dt. This is my CTFT. Now inverse Fourier transform, or I should write for your ease, inverse continuous time Fourier transform. So how do I recover my xt back? My x of t is from minus infinity to plus infinity, x of AF, this represent this f like this for ease, e raised to the power j 2 pi ft df. Okay, now when we talk about dtft, okay, so this is going to be a question for you. We already had discrete time Fourier transform. Why do we need discrete Fourier transform? Okay, so discrete time Fourier transform and discrete Fourier transform are two different quantities. Why do we need that? Again, I'll try and solve this query for you. So my discrete Fourier transform, x of omega from minus infinity to plus infinity, this is n is equals to x of n e raised to the power minus j omega n. Okay, now when we talk about, similarly in this case when we talk about z, so z is equal to e raised to the power j omega. That's it, that is the only replacement. So when I want to recover my x of n back, now I will see it's 1 by 2 pi minus infinity to plus infinity, or rather if I remember it correctly, it's minus pi to pi x of omega e raised to the power minus j omega n d omega. Oh, sorry, there's a mistake. D omega. Right. Now, if you can observe it, now this is purely on your basis of your observation. Even though we had x of n, even though we had x of n that is in discrete domain, yet my x of omega, when I want to recover my x of n back, is in continuous form. That is why we are using integration over here. So it doesn't solve my problem that we are going to still going to get infinite number of values, but there is a trick to it. These all values, the magnitude of x of omega is going to be periodic, and when we are talking about periodic, it might have a finite length to it. And when we are talking about finite length, that means for a periodic signal we can always create a, what we can say, sampling, and then we can get into the complete discrete domain. So here comes my discrete Fourier transform. Okay, so let us see what my DFT or discrete Fourier transform is all about. My DFT for a signal x of n, when I pass through a DFT filter, I get x of k. When I pass through its IDFT, I get x of n. So what is my x of k? My x of k is nothing but n is equals to 0 to n minus 1 x of n e raised to the power minus j2 pi k n by n, and k varying from 0, 1 to n minus 1. Class, do remember this thing. This is compulsory. If you're not going to mention it, if you're not going to mention this value of k, then your formula is going to be set as wrong, because if you see, there are two variables in it. One is n and another one is k. So x of k is going to depend on the variation of two variables n and k. So you need to define the limit for both the variables. So similarly, when we go for IDFT, what we get? We want to recover my x of n back. So I want my x of n for k standing from 0 to n minus 1. X of k e raised to the power j2 pi kn by n. Now we have got the limit for k. Similarly, we need limit for n to n minus 1. Okay, so this is your basic formulation of DFT and IDFTs. Okay, so in this whole unit, or we can say in this whole digital signal processing, we are going to be concentrated around DFT and IDFT in unit 1. Okay,